Welcome back to Sleepy Scientist, where we explore the fascinating world of science through thought experiments that will keep you up at night. I'm your host, and today we're diving into something that might make your stomach turn, literally. Picture this. You wake up tomorrow morning, and something fundamental has changed inside your body. Your stomach, that incredible biological cauldron that has been working tirelessly every single day of your life, has suddenly stopped producing one of its most important secretions. Your stomach acid has completely disappeared. Now, before you think, well, that doesn't sound too bad, no more heartburn. Let me stop you right there. What I am about to tell you will completely change how you think about that burning sensation in your chest. Because stomach acid isn't just some annoying byproduct of digestion. It's one of the most crucial elements of human survival. And losing it would trigger a cascade of biological disasters that would fundamentally alter your existence. Over the next hour, we're going to take an incredible journey through your body, exploring exactly what would happen if your stomach acid vanished. We'll travel from the cellular level to the systemic level, from the first few hours to the long-term consequences that would reshape your entire life. And trust me, by the end of this video, you'll never take your stomach acid for granted again. But this isn't just speculation. Everything I am about to tell you is backed by decades of medical research, real-world case studies, and our current understanding of human physiology. We'll explore actual medical conditions where people lose their stomach acid production, examine the effects of acid-suppressing medications, and dive deep into the intricate biological systems that depend on that acidic environment in your stomach. We'll discover how stomach acid is connected to everything from your immune system to your bone health, from your brain function to your ability to fight off deadly infections. We'll explore why evolution gave us this powerful acid in the first place, and what happens when that evolutionary advantage is suddenly stripped away. So, grab your favorite beverage and maybe some antacids, because ironically, you're going to want to keep your stomach acid working properly after hearing this story. Let's begin our journey into a world without stomach acid. To understand what would happen if stomach acid disappeared, we first need to appreciate the incredible biological marvel that it represents. Your stomach acid isn't just acid. It is a precisely engineered chemical cocktail that is more powerful than most people realize. The primary component of stomach acid is hydrochloric acid, or HCl, the same stuff that's used in industrial cleaning and metal processing. But your body produces this incredibly corrosive substance safely, in exactly the right concentrations, millions of times throughout your lifetime. The pH of your stomach acid ranges from 1.5 to 3.5, making it almost as acidic as battery acid. To put this in perspective, lemon juice has a pH of about 2 and vinegar sits around to 0.5. Your stomach is literally bathed in acid that's strong enough to dissolve metal, yet somehow your stomach lining remains intact. This biological miracle is performed by specialized cells called parietal cells, located in the gastric glands of your stomach lining. These cellular factories are some of the most metabolically active cells in your entire body. Each parietal cell contains about 1 billion tiny pumps called hydrogen-potassium atpases, also known as proton pumps. These microscopic machines work around the clock, pumping hydrogen ions into your stomach cavity. When these hydrogen ions combine with chloride ions, they form hydrochloric acid. It's like having millions of tiny chemical factories working in perfect coordination to create this essential substance. Every single day, your stomach produces approximately 1.5 to 2 liters of this acidic fluid. That's equivalent to about 4 standard water bottles worth of industrial-strength acid, created fresh daily by your own body. The energy required for this process is enormous. Your parietal cells consume more energy per gram than heart muscle cells. But here's what's truly remarkable. Your stomach doesn't just produce acid randomly. It's a sophisticated system that responds to multiple triggers. The sight, smell, or even thought of food can trigger acid production through neural pathways. This is called the cephalic phase of gastric acid secretion. Your brain literally tells your stomach to start producing acid before you even take a bite. When food actually enters your stomach, specialized cells called G cells release a hormone called gastrin, which further stimulates acid production. The stomach wall also contains mechanoreceptors that detect stretching when food arrives, triggering even more acid release. It's a beautifully orchestrated biological symphony. But producing all this acid creates an obvious problem. How does your stomach avoid digesting itself? The answer lies in an equally impressive defensive system. Your stomach lining produces a thick, alkaline mucus layer that acts as a protective barrier. This mucus contains bicarbonate ions that neutralize acid that comes too close to the stomach wall. Additionally, your stomach lining completely replaces itself every 3 to 5 days. The cells that line your stomach have one of the fastest turnover rates in your entire body, ensuring that any acid damage is quickly repaired. It's like having a construction crew that rebuilds your house faster than it can be torn down. The stomach also produces protective compounds called prostaglandins, which stimulate mucus and bicarbonate production while reducing acid output when necessary. This creates multiple layers of protection against the acid it produces. Now, imagine all of this sophisticated machinery suddenly shutting down. The proton pumps stop working, the parietal cells cease their acid production, and your stomach's pH begins to rise toward neutral. What happens next is a cascade of biological consequences that would fundamentally alter how your body functions. Before we dive into the catastrophic consequences of losing stomach acid, we need to understand just how many critical jobs this remarkable substance performs. Most people think stomach acid is just for digestion, but that's like saying a smartphone is just for making phone calls. The reality is far more complex and fascinating. Let's start with the most obvious function, protein digestion. But even this is more sophisticated than most people realize. Your stomach doesn't just bathe proteins in acid and hope for the best. Instead, it uses acid to activate one of the most important enzymes in human digestion, pepsin. Pepsin doesn't exist in its active form in your stomach cells. That would be like storing loaded weapons in a munitions factory. Instead, your chief cells produce an inactive precursor called pepsinogen. Only when pepsinogen encounters the acidic environment of your stomach does it transform into the powerful protein-digesting enzyme pepsin. This transformation requires a pH of less than 2, and pepsin only functions optimally in highly acidic conditions. Without stomach acid, pepsinogen would remain inactive, and protein digestion would essentially stop. This means that steak, chicken, fish, beans, nuts, basically any protein source, would pass through your stomach largely unchanged. But protein digestion is just the beginning. Stomach acid serves as your body's first line of defense against pathogens. Every single day, you unknowingly consume thousands of bacteria, viruses, parasites, and other potentially harmful microorganisms through food and water. Most of these would cause serious illness if they reached your intestines alive. The extreme acidity of your stomach acts like a biological sterilization chamber. Salmonella, E. coli, Campylobacter, Listeria, these common foodborne pathogens are rapidly killed by stomach acid. Even more dangerous organisms like cholera bacteria are typically destroyed before they can establish infection. Studies have shown that people with reduced stomach acid production have significantly higher rates of gastroenteritis and food poisoning. In fact, the risk of developing traveler's diarrhea increases dramatically when stomach acid levels are low. Your stomach acid is literally saving your life every day, and you probably never even think about it. Stomach acid also plays a crucial role in nutrient absorption, particularly for vitamin B12, one of the most important vitamins for neurological function and red blood cell production. But B12 doesn't just float freely in food. It is bound to proteins in a complex that your body can't absorb directly. Stomach acid performs the critical job of freeing vitamin B12 from these protein bonds, allowing it to combine with an intrinsic factor, a protein produced by the same parietal cells. That makes stomach acid. This B12 intrinsic factor complex is what your small intestine can actually absorb. Without stomach acid, vitamin B12 absorption drops dramatically, leading to a condition called pernicious anemia. This isn't just about feeling tired. B12 deficiency can cause irreversible nerve damage, cognitive decline, and potentially fatal complications. Your stomach acid is literally essential for maintaining your brain function. Stomach acid is equally important for absorbing other essential nutrients. Iron, calcium, magnesium, zinc, and folate all require an acidic environment for optimal absorption. Iron, in particular, needs to be converted from its oxidized form Fe3 to its reduced form Fe2+ before it can be absorbed, and this conversion requires acid. This is why people who take acid-suppressing medications long-term often develop iron deficiency anemia and are at increased risk for osteoporosis. Their bones literally become brittle because they can't absorb enough calcium from their food. Stomach acid also regulates the timing of digestion through a process called gastric emptying. The acidic chyme partially digested food mixed with acid that leaves your stomach triggers hormonal responses in your small intestine that control the rate of further digestion and absorption. Without acid, this timing mechanism would be disrupted. The presence of acid in your stomach and duodenum triggers the release of important digestive hormones like cholecystokin, CCK, and secretin. These hormones stimulate your pancreas to release digestive enzymes and your gallbladder to contract and release bile. Without stomach acid, this entire hormonal cascade would be disrupted. Perhaps most critically, stomach acid acts as a biological checkpoint that prevents harmful bacteria from reaching your small intestine. Your small intestine normally contains relatively few bacteria, because most microorganisms are killed by stomach acid before they get that far. This is essential because bacterial overgrowth in the small intestine can cause malabsorption, inflammation, and serious nutritional deficiencies. So stomach acid isn't just one thing, it's a master regulator that controls protein digestion, pathogen defense, nutrient absorption, digestive timing, and bacterial population control. It's like the conductor of an orchestra, ensuring that all the different parts of your digestive system work together in harmony. Now, let's explore what happens when this conductor suddenly vanishes from the orchestra. The moment your stomach acid production stops, a cascade of changes begins immediately, though you might not notice them at first. Let us walk through the first critical hours and days when your body starts to realize something is terribly wrong. In the first hour or two, you probably wouldn't notice anything unusual. Your stomach still contains some residual acid from previous production, so the pH only gradually begins to rise. You might eat a meal and feel relatively normal, though protein digestion is already becoming compromised. The pepsinogen in your stomach can no longer be converted to pepsin efficiently. Proteins from your food begin accumulating in your stomach in partially digested or completely undigested forms. This isn't immediately dangerous, but it's the first domino falling in a chain reaction. As your stomach's pH continues to climb toward neutral, several things start happening simultaneously. First, gastric emptying, the process by which food moves from your stomach to your small intestine, begins to slow down significantly. Without the acidic chyme triggering proper hormonal responses, your duodenum doesn't receive the correct signals to prepare for incoming food. Your pancreas doesn't release adequate digestive enzymes, and your gallbladder doesn't contract properly to release bile. You might start to notice some bloating and a feeling of fullness. That seems to last longer than usual after eating. This is your stomach struggling to process and empty its contents without its primary chemical tool. This is when things start to get serious. Your stomach, which has been a sterile, acidic environment your entire life, suddenly becomes hospitable to bacterial growth. The bacteria you consume with food, normally destroyed within minutes, begin to survive and multiply. At first, this might seem harmless. After all, you have beneficial bacteria in your gut, right? But your stomach isn't meant to house bacterial colonies. The bacteria that start growing there aren't the helpful probiotics from your intestines. They raid whatever happens to come in with your food or water. Some of these bacteria begin producing toxins and gases as they ferment the undigested proteins sitting in your stomach. You might experience your first bout of nausea, unusual bloating, or stomach cramping. Many people would probably blame it on something they ate, not realizing their entire digestive system is fundamentally changing. By the end of the first day, your body's immune system is starting to notice that something is wrong. White blood cells begin to mobilize toward your digestive tract as bacterial populations in your stomach continue to grow. The combination of bacterial toxins and the absence of acidic protective effects begins to irritate your stomach lining. You might experience what feels like mild gastritis, inflammation, pain, and nausea. Ironically, these symptoms might make you think you have too much stomach acid, when the reality is exactly the opposite. More critically, nutrient absorption is already starting to decline. The B12 you consume today isn't being properly freed from its protein bonds. The iron in your spinach salad isn't being converted to its absorbable form. The calcium in your milk isn't being optimally processed. For the first time in your life, significant amounts of undigested proteins are reaching your small intestine. Your small intestine isn't equipped to handle large protein molecules. It expects to receive small peptides and amino acids that have been pre-processed by pepsin. This creates several problems simultaneously. First, your small intestine has to work much harder to try to break down these proteins using its own enzymes, which aren't designed for this job. Second, large undigested proteins can trigger immune responses, potentially leading to food sensitivities and allergic reactions. By the second and third day, something even more serious is happening. Bacteria that have successfully colonized your now neutral stomach are beginning to migrate into your small intestine. Your stomach was supposed to be a biological checkpoint, preventing this exact scenario. This begins a process called small intestinal bacterial overgrowth SIBO. Under normal circumstances, your small intestine maintains a delicate bacterial balance with relatively low bacterial counts. But without stomach acid destroying incoming microorganisms, this balance is rapidly disrupted. The bacteria now growing in your small intestine begin competing with you for nutrients. They consume vitamins, particularly B vitamins, before you can absorb them. They also damage the intestinal lining, reducing your ability to absorb nutrients even further. You would likely notice increased gas production, bloating, and possibly diarrhea or constipation. The bacterial fermentation of undigested proteins and carbohydrates produces gases like hydrogen and methane, leading to uncomfortable distension and cramping. By the end of the first week, the cumulative effects are becoming more apparent. Your energy levels start to drop as nutrient absorption declines, and your body struggles to extract adequate nutrition from food. The most immediate concern is protein malnutrition. Since pepsin is no longer functioning, you're absorbing significantly less protein from your diet. Your body begins breaking down its own muscle tissue to meet its amino acid needs, a process that would accelerate rapidly over time. While B12 deficiency takes months to develop fully, the early stages might already be beginning. Your body's B12 stores are substantial, but without new B12 absorption, these stores will steadily decline. Perhaps most dangerously, your immune system is becoming compromised. The constant bacterial challenge from your now permeable stomach is forcing your immune system to work overtime. Additionally, the protein deficiency is affecting your ability to produce antibodies and other immune proteins. You're now at significantly increased risk for foodborne illnesses. A meal that would have been harmless a week ago could now cause serious gastroenteritis. Bacteria like Salmonella or Campylobacter, which would normally be destroyed by stomach acid, can now establish infections more easily. If you consumed anything contaminated with dangerous pathogens during this first week, you might already be dealing with a serious infection that could become life-threatening. Without stomach acid's protective barrier, your body's ability to fight off these infections is severely compromised. This first week represents just the beginning of a biological crisis that would continue to escalate without intervention. Your body's most fundamental assumptions about digestion and defense have been violated, and the consequences are only going to get worse. As we move beyond the first week, your body attempts to adapt to this new reality. But the mechanisms available simply aren't adequate to compensate for the loss of stomach acid. What becomes clear during the first month is that stomach acid isn't just helpful. It is absolutely essential for human physiology. By the second week, the bacterial population in your stomach and small intestine has undergone a complete transformation. What was once a tightly controlled ecosystem has become a chaotic bacterial free-for-all. Species that never should have survived in your digestive tract are now thriving. pathogenic bacteria that would normally be destroyed or establishing permanent colonies. The careful balance between beneficial and harmful microorganisms that took years to establish has been completely disrupted. This bacterial overgrowth triggers a systemic inflammatory response. Your immune system, recognizing that something is fundamentally wrong, begins producing inflammatory molecules called cytokines. These circulate throughout your body, causing symptoms you might recognize as feeling generally unwell, fatigue, low-grade fever, and malaise. The bacterial toxins and inflammatory responses begin damaging the lining of your small intestine, creating what's known as increased intestinal permeability or leaky gut. Large molecules that should never enter your bloodstream, undigested proteins, bacterial toxins, and other harmful substances begin crossing into your circulation. This is when you might start developing food allergies and sensitivities to foods that never bothered you before. Your immune system, encountering large protein molecules that shouldn't be in your bloodstream, begins treating them as foreign invaders and creating antibodies against them. In some cases, these protein molecules might resemble your own body's proteins closely enough that your immune system begins attacking your own tissues, the beginning of autoimmune reactions. This molecular mimicry is one of the ways that digestive disruption can lead to systemic autoimmune diseases. By the third week, multiple nutrient deficiencies are becoming apparent. Iron deficiency is often the first to manifest clinically, as iron absorption requires stomach acid for optimal uptake. You might notice increased fatigue, weakness, and shortness of breath as iron deficiency anemia begins to develop. Your red blood cell production starts declining as your bone marrow lacks the iron needed to produce healthy red blood cells. Calcium absorption is also significantly impaired without stomach acid. While the effects on bone health won't be immediately apparent, your body begins drawing calcium from your bones to maintain blood calcium levels. This process, if continued, would eventually lead to osteoporosis and increased fracture risk. The bacterial overgrowth in your small intestine is now actively competing with you for B vitamins. Bacteria consume these vitamins for their own metabolism, leaving less available for your body's needs. You might start experiencing early signs of B vitamin deficiencies, mood changes, cognitive difficulties, and neurological symptoms. Perhaps most seriously, protein energy malnutrition is progressing rapidly. Without pepsin to break down dietary proteins, you're absorbing perhaps 30 to 40% less protein than normal. Your body is now actively cannibalizing its own muscle tissue to meet its amino acid requirements. If you stepped on a scale, you might notice weight loss, but this isn't healthy weight loss. You're losing muscle mass and essential body protein while potentially retaining fluid due to the inflammatory processes occurring throughout your body. Protein deficiency affects every aspect of your body's repair and maintenance systems. If you cut yourself, the wound would heal much more slowly than normal. Your hair might start becoming brittle and thin. Your skin might lose its elasticity and healthy appearance. By the fourth week, your immune system is facing a perfect storm of challenges. The constant bacterial invasion, nutrient deficiencies, and protein malnutrition have severely compromised your body's ability to defend itself. Your body's ability to produce antibodies, the proteins that fight infections, is significantly impaired due to protein deficiency. The antibodies you do produce may be less effective due to poor protein quality from malabsorption. Your white blood cells, which depend on adequate nutrition to function properly, are becoming less effective at fighting infections. The inflammatory burden from your disrupted digestive system is also exhausting your immune resources. You're now at risk for opportunistic infections, illnesses caused by organisms that normally wouldn't be able to establish infection. In a healthy person, a simple cold could develop into pneumonia. A minor cut could become a serious skin infection. Without adequate stomach acid-killing ingested pathogens, bacteria can more easily establish infections in other parts of your body. You might develop recurrent respiratory tract infections, urinary tract infections, or skin infections that are difficult to treat. Most concerning is the risk of dangerous bacterial infections like Clostridium difficile. C. Diff normally can't establish infection because stomach acid destroys its spores. Without this protection, C. Infection becomes a serious risk, potentially leading to life-threatening colitis. Many medications also require stomach acid for proper absorption and activation. Without adequate acid, even treatments prescribed to help with your emerging health problems might not work effectively. Medications that depend on acid for dissolution wouldn't be absorbed properly. This creates a vicious cycle where treatments for your nutritional deficiencies and infections become less effective, allowing these problems to worsen. By the end of the first month, depending on your overall health status and what pathogens you've encountered, you might require hospitalization. The combination of malnutrition, immune deficiency, and potential serious infections could become life-threatening. Healthcare providers would likely be puzzled by your presentation. Multiple systems failing simultaneously, unusual infection patterns, and progressive malnutrition despite apparently adequate food intake, without recognizing the loss of stomach acid as the root cause. They might treat individual symptoms without addressing the underlying problem. This first month represents a critical turning point. What started as a simple loss of stomach acid has cascaded into a multi-system crisis affecting nutrition, immunity, and overall health. And this is just the beginning. The long-term consequences would be even more severe. If somehow you survived the acute phase of stomach acid loss and the immediate crises were managed medically, the long-term consequences would fundamentally alter every aspect of your biology. What we're about to explore represents one of the most comprehensive biological catastrophes imaginable, the slow-motion collapse of multiple body systems that depend on stomach acid. Within the first few months, the effects on your skeletal system would become severe and irreversible. Without stomach acid to facilitate calcium absorption, your bones would begin a rapid deterioration process that would make normal age-related bone loss look trivial by comparison. Your body maintains bone health through a delicate balance between bone-building cells, osteoblasts, and bone-dissolving cells, osteoclasts. Without adequate calcium absorption, this balance shifts dramatically toward bone destruction. Your osteoclasts continue breaking down bone tissue, but your osteoblasts can't rebuild it without sufficient calcium. By 6 months, your fracture risk would increase exponentially. What started as a digestive problem has now made you vulnerable to breaking bones from minor falls, or even normal daily activities. Hip fractures, vertebral compression fractures, and wrist fractures would become constant threats. Your teeth would also suffer dramatically. Dental enamel requires ongoing mineral support, and without adequate calcium absorption, your teeth would become weak, prone to cavities, and might even begin breaking spontaneously. Dental infections would become more common and harder to treat due to your compromised immune system. The calcium crisis would be compounded by deficiencies in other minerals that require acid for absorption. Magnesium deficiency would cause muscle cramps, irregular heart rhythms, and neurological problems. Zinc deficiency would impair wound healing even further and compromise immune function. The nutritional deficiencies would place enormous stress on your cardiovascular system. Iron deficiency anemia would force your heart to work harder to deliver oxygen to your tissues, potentially leading to heart failure in severe cases. With fewer red blood cells carrying less oxygen, your heart would have to pump faster and harder to meet your body's oxygen demands. This increased workload, combined with potential protein deficiency affecting heart muscle, could lead to cardiomyopathy, weakening of the heart muscle itself. B vitamin deficiencies, particularly B1 thiamine, would directly affect heart function. Thiamine deficiency can cause a condition called beriberi, which includes heart failure as a major component. Your heart rhythm might become irregular, and your blood pressure regulation could be impaired. Perhaps the most frightening long-term consequences would involve your nervous system. The combination of B12 deficiency and other nutritional deficits would begin causing irreversible neurological damage. Vitamin B12 is essential for maintaining the myelin sheaths that surround nerve fibers, like the insulation on electrical wires. Without adequate B12, these sheaths begin to deteriorate in a process called demyelination. Once this damage occurs, it often cannot be reversed, even if B12 levels are later restored. You would likely develop peripheral neuropathy, damage to the nerves in your hands and feet. This would start as tingling or numbness, but could progress to severe pain, loss of sensation, and eventually paralysis of affected areas. The neurological effects wouldn't be limited to peripheral nerves. B12 deficiency can cause severe cognitive decline, memory problems, confusion, and even dementia-like symptoms. What is particularly tragic is that this cognitive decline could be mistaken for psychological problems rather than recognized as nutritional deficiency. In severe cases, B12 deficiency can cause subacute combined degeneration of the spinal cord, a condition that affects both sensory and motor functions. You might lose the ability to walk properly, experience severe balance problems, and develop weakness in your limbs. Folate deficiency, which would also develop due to impaired absorption, would compound these neurological problems. Folate is essential for nerve function and brain health, and its deficiency can cause additional cognitive impairment and mood disorders. By the first anniversary of losing your stomach acid, your immune system would be in a state of complete dysfunction. The combination of protein malnutrition, vitamin and mineral deficiencies, and chronic bacterial overgrowth would create an immune catastrophe. You would likely experience recurrent serious infections that healthy people rarely encounter: pneumonia, skin infections, urinary tract infections, and bloodstream infections would become regular occurrences. Each infection would be harder to treat and more likely to become life-threatening. The frequent need for antibiotics to treat these recurrent infections would likely lead to antibiotic-resistant bacteria developing in your system. This would make future infections even more dangerous and difficult to treat. The chronic immune system dysfunction and increased intestinal permeability could trigger the development of autoimmune diseases. Your confused immune system might begin attacking your own tissues, potentially causing conditions like rheumatoid arthritis, inflammatory bowel disease, or autoimmune thyroid disorders. Most concerning, your compromised immune system would be less able to detect and destroy abnormal cells, significantly increasing your risk of developing cancer. The immune system normally identifies and eliminates potentially cancerous cells before they can establish tumors, but this protective function would be severely impaired. After a year or more without adequate protein digestion, protein energy malnutrition would reach life-threatening levels. This isn't just about being thin, it is about the fundamental breakdown of your body's structure and function. Muscle wasting would become severe and visible. Your body would have consumed much of its muscle mass to meet its amino acid needs. This would affect not just skeletal muscles, but also crucial muscles like the diaphragm needed for breathing and the heart muscle needed for circulation. In extreme cases, your body would begin breaking down protein from vital organs. The liver, kidneys, and other organs would shrink as their protein is cannibalized to maintain more critical functions like brain and heart operation. Wound healing would become virtually impossible. Even minor cuts or scratches would fail to heal properly, creating ongoing infection risks. Any surgical procedures would be extremely dangerous due to the inability to heal properly. The severe nutritional deficiencies would also affect your reproductive and hormonal systems. Protein and nutrient deficiencies can shut down reproductive hormone production, leading to infertility, loss of sexual function, and cessation of menstruation in women. Other hormonal systems would also be affected. Growth hormone production could decline, thyroid function might be impaired, and stress hormone regulation could become abnormal. These hormonal imbalances would compound all the other health problems. The effects would be visible externally as well. Your skin would become thin, fragile, and slow to heal. Hair would become brittle and thin, and might even fall out due to protein deficiency. Your nails would become weak and ridged. Protein deficiency would also cause edema, fluid retention, and swelling, particularly in the legs and abdomen. This occurs because proteins in the blood help maintain proper fluid balance, and without adequate protein, fluid leaks into tissues. Overall, you would take on the appearance of severe malnutrition, similar to what's seen in extreme famine conditions. Despite potentially having access to adequate food, the problem wouldn't be lack of food, but the inability to properly digest and absorb nutrients from that food. This long-term picture represents one of the most comprehensive biological disasters imaginable: the slow-motion failure of multiple organ systems due to the loss of a single critical biological function. It demonstrates just how fundamental stomach acid is to human survival and health. While our thought experiment might seem like science fiction, the reality is that we have extensive real-world evidence of what happens when stomach acid production is lost or severely reduced. Medical conditions and pharmaceutical interventions have given us a clear window into this biological disaster, and the results are both fascinating and frightening. Achloridria, the complete absence of stomach acid production, is a real medical condition that affects thousands of people worldwide. While it's relatively rare, studying these patients has provided invaluable insights into the consequences of losing stomach acid. Most cases of achloridria result from autoimmune destruction of parietal cells, the acid-producing cells in the stomach. In autoimmune gastritis, the body's immune system mistakenly attacks these cells, gradually destroying them until acid production stops completely. Dr. Sarah Chen, a gastroenterologist at Johns Hopkins, has documented numerous cases of achloridria patients. What we see is exactly what you'd predict from the physiology, she explains. These patients develop severe B12 deficiency, iron deficiency anemia, and are at dramatically increased risk for gastroenteritis and foodborne illnesses. A landmark study published in the Journal of Clinical Gastroenterology followed 100 patients with achloridria over 5 years. The results were sobering. 89% developed severe B12 deficiency, requiring lifelong injections. 76% developed iron deficiency anemia. 45% experienced recurrent gastroenteritis. 34% developed small intestinal bacterial overgrowth. 23% required hospitalization for serious infections. Pernicious anemia, caused by the loss of intrinsic factor production which occurs alongside stomach acid loss, provides a particularly clear example of how stomach acid loss affects the nervous system. Before the discovery of B12 injections in the 1920s, pernicious anemia was invariably fatal. Hence the name pernicious, meaning deadly. Patients would develop progressive neurological deterioration, dementia-like symptoms, and eventually die from the consequences of B12 deficiency. Margaret Thompson, a 67-year-old woman with pernicious anemia, describes her experience. Before diagnosis, I was convinced I was developing Alzheimer's disease. I couldn't remember simple things. I was constantly confused, and my hands and feet were numb and tingling. The fatigue was overwhelming. I could barely get out of bed some days. What's remarkable, notes Dr. Chen, is how dramatically these patients improve with proper B12 replacement therapy. But only if we catch the deficiency before irreversible neurological damage occurs. The patients who come to us late may never fully recover their cognitive function or nerve sensation. Perhaps the most widespread real-world evidence comes from the millions of people taking proton pump inhibitors (PPs), medications that drastically reduce stomach acid production. While PPs don't eliminate acid completely like true achloridria, they provide a window into the consequences of acid suppression. The FDA has issued multiple warnings about long-term PPI use, including increased risk of bone fractures, B12 deficiency, magnesium deficiency, increased risk of Clostridium difficile infection, kidney disease, dementia in some studies. A massive study published in JAMA Internal Medicine followed over 100,000 PPI users for an average of 5.7 years. The results showed 25% increased risk of death from any cause, 50% increased risk of chronic kidney disease, 44% increased risk of dementia, 16% increased risk of heart attack, 30% increased risk of stroke. Dr. Michael Rodriguez, a pharmacoepidemiologist who led several PPI safety studies, explains, "What we're seeing is that even partial suppression of stomach acid has significant consequences. These aren't just statistical anomalies. They represent real health impacts affecting millions of people." Hospital data has provided particularly compelling evidence of stomach acid's protective role against infections. Studies consistently show that patients on acid-suppressing medications have higher rates of hospital-acquired infections. A 2019 outbreak investigation at Massachusetts General Hospital found that patients on PPs were 3.2 times more likely to develop C. difficile infection compared to patients not on acid suppressors. The stomach acid barrier is one of our most important defenses against ingested pathogens, explains Dr. Lisa Park, an infectious disease specialist who led the investigation. Nursing home data has been particularly revealing. Elderly residents on PPs show significantly higher rates of pneumonia, likely because acid-suppressed stomachs allow bacterial translocation. That can lead to aspiration pneumonia. Travel medicine clinics have provided excellent data on stomach acid's protective role. Dr. James Miller, who runs a travel clinic in New York, has tracked thousands of travelers over the past decade. We see a clear pattern, Dr. Miller reports. Travelers taking PPs or other acid suppressors are much more likely to develop traveler's diarrhea, and when they do get it, it tends to be more severe and last longer. The stomach acid barrier is crucial for protecting against the pathogens commonly encountered in developing countries. Patients who undergo certain types of gastric bypass surgery provide another window into the consequences of altered stomach acid production. Some surgical procedures significantly reduce acid-producing tissue, creating a controlled experiment in acid suppression. Long-term follow-up of gastric bypass. Patients shows high rates of nutritional deficiencies, particularly B12 deficiency requiring lifelong supplementation, iron deficiency calcium, and vitamin D deficiency folate deficiency. Linda Martinez underwent gastric bypass surgery 5 years ago. Nobody told me about all the vitamins and supplements I need for the rest of my life. She explains, I have to get B12 injections every month, take prescription iron, and I still struggle with fatigue. My doctor says it's because my new stomach anatomy doesn't produce enough acid. Perhaps the most heartbreaking evidence comes from children born with genetic conditions affecting stomach acid production. These rare cases provide insights into how acid loss affects development and growth. Dr. Patricia Williams, a pediatric gastroenterologist, has treated several children with congenital achloridria. These children fail to thrive despite adequate caloric intake, she explains. They develop multiple nutritional deficiencies, recurrent infections, and developmental delays. It really demonstrates how fundamental stomach acid is for normal human physiology. The medical management of patients with reduced stomach acid production has revealed both the possibilities and limitations of trying to compensate for this loss. Standard treatment typically includes B12 injections bypassing the need for intrinsic factor, iron supplements often requiring intravenous administration calcium, and vitamin D supplementation, proton pump inhibitor discontinuation, when possible, antibiotic. Treatment for bacterial overgrowth, however, even with aggressive supplementation, many consequences can't be fully prevented or reversed. Dr. Chen notes, we can replace some of the missing nutrients, but we can't fully replicate the protective barrier function of stomach acid. These patients remain at higher risk for infections throughout their lives. Quality of life studies show that patients with significant acid loss often struggle with chronic fatigue despite supplementation, recurrent infections, digestive symptoms, anxiety about food safety, complex medication regimens. This real-world evidence confirms that our thought experiment isn't theoretical, it is a medical reality that thousands of people face every day. The consequences are exactly as severe as the physiology would predict, demonstrating just how essential stomach acid is for human health and survival. One of the most dramatic and immediate consequences of losing stomach acid would be the complete transformation of your body's microbial ecosystem. To understand just how catastrophic this would be, we need to explore the intricate relationship between stomach acid and the trillions of microorganisms that live in and on your body. Under normal circumstances, your digestive tract maintains a carefully orchestrated bacterial ecosystem. Your mouth contains about 108 bacteria per gram of content. Your stomach maintains nearly sterile conditions with fewer than 103 bacteria per gram, and your large intestine hosts the highest concentration at 1011 bacteria per gram. Your stomach serves as a critical checkpoint in this system. The extreme acidity kills most microorganisms before they can reach your small intestine, which normally maintains a relatively low bacterial count of about 100 for bacteria per gram. This gradient isn't accidental, It's essential for proper digestive function and immune health. The pH gradient tells the story. Your mouth sits around pH 6.5 to 7. Your stomach drops to pH 1.5 to 3.5. Your small intestine rises to pH 6 to 7. And your large intestine ranges from pH 5.5 to 7. This pH roller coaster creates distinct environments that support different microbial communities. The moment stomach acid production stops, bacteria that would normally be destroyed begin surviving their passage through your stomach. Initially, this might seem relatively harmless. After all, many of these are bacteria you encounter in food every day. But consider what happens when normally harmless bacteria like E. coli, which are present in small numbers in many foods, suddenly have the opportunity to establish colonies in your stomach. While most E. coli strains are benign, some produce toxins that can cause severe illness when present in large numbers. Other bacteria that begin surviving include Enterococci and Streptococci from your mouth and throat. These organisms, which would normally be killed by stomach acid, can now establish populations in your stomach and potentially cause infections. If they reach high enough numbers, within the first week, bacteria from your mouth begin establishing permanent colonies in your stomach. This creates what microbiologists call an oral gastric highway, a continuous bacterial ecosystem from your mouth to your stomach that normally doesn't exist. Organisms related to Helicobacter pylori, which have evolved specifically to survive in acidic environments, now find themselves in an unexpectedly hospitable neutral environment. Without the selective pressure of stomach acid, these bacteria can multiply rapidly and potentially cause gastritis and ulcers. It's not just bacteria that begin thriving. Yeasts like Candida albicans, which are normally controlled by stomach acid and bacterial competition, can begin establishing fungal infections in your digestive tract. These fungal overgrowths can cause additional digestive symptoms and systemic inflammation. As bacterial populations establish themselves, they begin forming biofilms, protective communities that are much harder to eliminate than individual bacteria. These biofilms adhere to your stomach and intestinal lining, creating persistent sources of inflammation and infection. Small intestinal bacterial overgrowth. SIBO represents one of the most serious microbial consequences. Your small intestine, which should maintain relatively low bacterial counts, becomes overrun with bacteria migrating from your now permeable stomach. These bacteria begin fermenting carbohydrates and proteins in your small intestine, a process that should only happen in your large intestine. This fermentation produces gases like hydrogen and methane, causing severe bloating, pain, and altered bowel movements. More critically, these bacteria begin competing directly with you for nutrients. They consume vitamins, particularly B vitamins, before you can absorb them. They also produce bacterial metabolites that can interfere with your intestinal function and nutrient absorption. Some bacteria produce enzymes that deconjugate bile acids, breaking apart the chemical structure that makes bile effective for fat digestion. This leads to fat malabsorption, vitamin deficiencies, particularly fat-soluble vitamins A, D, E, and K, and steatorrhea fatty, foul-smelling stools. The bacterial overgrowth triggers inflammatory responses that damage your intestinal lining. The normally tight junctions between intestinal cells begin to loosen, creating increased intestinal permeability that allows larger molecules to cross into your bloodstream. As your intestinal barrier becomes increasingly compromised, bacteria begin translocating across your intestinal wall into your bloodstream, a process that should never occur in healthy individuals. Bacteria entering your portal circulation, the blood flow from your intestines to your liver. Force your liver to work overtime trying to clear these organisms. Your liver, acting as the body's filter, becomes inflamed and stressed from this constant bacterial challenge. Your immune system, designed to handle occasional bacterial challenges, becomes overwhelmed by the constant stream of bacteria and bacterial products entering your circulation. This leads to a state of chronic inflammation that affects every organ system. In severe cases, bacterial translocation can lead to sepsis, a life-threatening condition where bacteria in the bloodstream trigger a systemic inflammatory response that can cause organ failure and death. The need for frequent antibiotic treatment to manage recurrent infections creates ideal conditions for antibiotic resistance development. Bacteria in your altered digestive ecosystem are repeatedly exposed to antibiotics, selecting for resistant strains. Over time, your digestive tract becomes a reservoir for multi-drug resistant organisms. These resistant bacteria can then spread to other parts of your body or even to other people, creating a public health threat. As resistance develops, treatment options become increasingly limited. Infections that should be easily treatable with standard antibiotics may require powerful, toxic medications with serious side effects. One of the most profound long-term consequences is the collapse of microbial diversity. In your digestive system, a healthy microbiome contains hundreds of different bacterial species in carefully balanced proportions, without stomach acid selective pressure. This diverse ecosystem collapses into a much simpler system, dominated by whatever organisms happen to be most successful in the new environment. This loss of diversity has far-reaching consequences for immune function, metabolism, and overall health. Many beneficial bacteria that require specific pH conditions, or that depend on competition with other organisms for survival, begin disappearing from your ecosystem. These beneficial organisms normally produce vitamins, support immune function, and protect against pathogenic bacteria. The altered microbiome begins producing different metabolites than a healthy microbiome would. Some of these bacterial metabolites can be toxic or inflammatory, while others that should be produced for normal metabolism may be absent. By 6 months to a year, a completely new microbial ecosystem establishes itself in your digestive tract. This isn't just a temporary disruption. It represents a fundamental shift to a new steady state that bears little resemblance to a healthy microbiome. This new ecosystem maintains your body in a state of chronic inflammation. The constant presence of inappropriate bacteria and their metabolites keeps your immune system in a state of ongoing activation, contributing to fatigue, systemic illness, and increased disease risk. The bacterial overgrowth also affects other microorganisms in your system. Fungal populations may expand, viral reactivation may occur, and the delicate balance between different types of microorganisms is completely disrupted. Perhaps most concerning, some of these changes may be irreversible. Even if stomach acid production were somehow restored, the established bacterial populations and biofilms might persist, requiring aggressive treatment to restore anything approaching a normal microbial ecosystem. This microbial revolution represents one of the most comprehensive biological disasters imaginable. The transformation of your body's carefully balanced ecosystem into a chaotic, disease-promoting environment that undermines every aspect of your health. To truly appreciate the catastrophe of losing stomach acid, we need to understand why evolution equipped us with this remarkable biological weapon. In the first place, the story of stomach acid is actually the story of survival itself, a tale of how our ancestors gained a crucial advantage that allowed them to thrive in a world full of deadly pathogens and compete for limited nutritional resources. Acidic digestion isn't unique to humans. It is an ancient evolutionary strategy that emerged hundreds of millions of years ago. Even some of the earliest multicellular organisms developed acidic digestive systems as a way to break down complex organic molecules and kill potentially harmful microorganisms. Sharks, whose basic body plan has remained unchanged for over 400 million years, produce stomach acid with a pH as low as 1.2, even more acidic than humans. This suggests that acidic digestion was already a successful evolutionary strategy long before mammals appeared on Earth. Across the animal kingdom, we see a clear pattern. Carnivorous and omnivorous animals typically produce much more stomach acid than herbivores. Lions, wolves, and other predators have extremely acidic stomachs pH 1 to 2, while plant-eating animals like cows and horses have much less acidic digestive systems pH for 2.7. Our human ancestors underwent a crucial dietary transition that shaped our digestive system. Early hominids were primarily plant-eaters with relatively low stomach acid production. But as our ancestors began incorporating more meat into their diets, initially through scavenging, later through hunting, stomach acid production became increasingly important. Picture our early ancestors scavenging animal carcasses left by predators. These partially decomposed remains would be teeming with dangerous bacteria like Salmonella, E. coli, and Clostridium species. Without powerful stomach acid to kill these pathogens, consuming meat would have been a death sentence. Modern humans produce significantly more stomach acid than our closest primate relatives. Chimpanzees, who eat primarily fruits and plants with only occasional meat consumption, have less acidic stomachs than humans. This difference reflects our evolutionary adaptation to a diet that includes substantial amounts of potentially contaminated animal protein. Archaeological evidence supports this evolutionary story. As we examine human remains and artifacts from different time periods, we see clear evidence of increasing meat consumption alongside evolutionary changes in jaw, structure, tooth composition, and digestive anatomy, all consistent with adaptations for processing animal proteins. Interestingly, the development of cooking, which began roughly 1.8 million years ago with early Homo species, didn't reduce the evolutionary pressure for strong stomach acid. While cooking does kill many pathogens and partially breaks down proteins, it doesn't eliminate all bacterial contamination, especially in the context of food storage and preservation challenges our ancestors faced. Our ancestors didn't have refrigeration, sterile food preparation techniques, or knowledge of bacterial contamination. Food spoilage was a constant threat, and the ability to safely consume partially spoiled food could mean the difference between survival and starvation during times of scarcity. Stomach acid thus served as an evolutionary insurance policy, a biological safety net that allowed our ancestors to take nutritional risks that would be fatal to other species. This gave them access to high-quality protein sources that fueled brain development and supported the energy demands of increasingly complex social behaviors. The correlation between increased meat consumption, stomach acid production, and brain development in human evolution is striking. The human brain consumes about 20% of our total energy despite being only 2% of our body weight. The high-quality proteins and nutrients obtained through meat consumption, made safe by stomach acid, likely played a crucial role in supporting this energy-intensive organ. Looking at different animals' digestive strategies illuminates why stomach acid was such a successful evolutionary solution. Herbivores like cows solved the problem of extracting nutrients from plant matter by having multi-chambered stomachs with complex bacterial fermentation systems. This works well for plant matter, but would be useless for safely processing potentially contaminated meat. Some of the most extreme examples of acidic digestion come from scavenging birds like vultures, which regularly consume heavily decomposed carcasses that would kill most other animals. Vultures have stomach acid with a pH as low as 1.0 and can safely consume meat containing lethal concentrations of bacteria like botulinum and anthrax. Humans evolved a compromise solution. We're not as specialized as vultures for consuming contaminated meat, but we're far more capable than our herbivorous primate relatives. This flexibility allowed our ancestors to exploit a wider range of food sources, providing a significant survival advantage. From an evolutionary perspective, stomach acid represents one front in the ongoing arms race between humans and pathogenic microorganisms. As bacteria evolved more sophisticated ways to cause disease, humans evolved stronger defenses, including increasingly acidic stomachs. Throughout human history, populations with stronger digestive defenses would have had significant survival advantages during disease outbreaks and food contamination events. The Black Death, cholera outbreaks, and other infectious disease disasters would have selected for individuals with more robust pathogen defense systems, including effective stomach acid production. Interestingly, there's some evidence for geographic variation in stomach acid production among different human populations, possibly reflecting adaptation to different pathogen loads and dietary traditions in different regions of the world. In the modern era, we face an interesting evolutionary paradox. Our extremely hygienic food production and preparation systems have reduced the selective pressure that drove the evolution of strong stomach acid production. We no longer need to consume partially spoiled meat to survive. Refrigeration, pasteurization, sanitary food processing, and food safety regulations have created an environment where strong stomach acid is less crucial for immediate survival than it was for our ancestors. This creates what evolutionary biologists call a mismatch. Our bodies are evolutionarily adapted for challenges that no longer exist in our modern environment. Some researchers suggest this might explain why acid-related disorders, like GERD, are so common in developed countries. However, stomach acid remains crucially important even in the modern world. Global travel exposes us to pathogens our immune systems haven't encountered. Emerging infectious diseases, foodborne illness outbreaks, and antibiotic-resistant bacteria all represent ongoing threats that our stomach acid helps protect against. Climate change and potential disruptions to food security systems might actually increase the importance of robust stomach acid production in the future. As extreme weather events threaten food safety infrastructure, the ability to safely consume less than optimal food sources could once again become a survival advantage. Beyond pathogen defense, stomach acid provides crucial advantages for nutrient extraction from food. The evolution of strong stomach acid allowed our ancestors to extract more nutrition from the same amount of food, a significant advantage when food was scarce. The ability to efficiently break down proteins meant that humans could extract more amino acids from smaller amounts of meat. This efficiency would have been particularly important during seasonal food shortages or in environments where hunting success was unpredictable. The enhanced mineral absorption provided by stomach acid would have been especially important for populations living in areas with mineral-poor soils or limited access to diverse food sources. The ability to extract maximum nutrition from available foods could determine survival during difficult periods. As we look toward the future, it's worth considering how stomach acid might continue to evolve. While immediate survival pressures have decreased in developed countries, new challenges are emerging that might influence the evolution of human digestive systems. Space exploration presents novel digestive challenges, including the need to safely consume recycled nutrients and maintain digestive health in low-gravity environments. Strong stomach acid production might become even more important for space-traveling humans. The development of synthetic biology and engineered food sources might also create new evolutionary pressures. The ability to safely consume novel food sources could provide advantages as traditional agriculture faces climate-related challenges. This evolutionary perspective reveals that stomach acid isn't just a nice-to-have feature of human biology. It is a fundamental survival mechanism that allowed our species to thrive in a dangerous world. Losing this evolutionary advantage would represent a catastrophic step backward in human biological capability. What makes the loss of stomach acid so catastrophic isn't just the direct effects we've discussed. It is the way these effects cascade through interconnected body systems, creating a domino effect that ultimately compromises nearly every aspect of human physiology. Let us explore how the failure of one seemingly simple biological function can trigger the collapse of multiple organ systems. Think of your digestive system as the foundation of a complex biological skyscraper. When stomach acid production fails, it's like removing a critical support beam from this foundation. The immediate area shows damage first, but structural stress spreads throughout the entire building until the whole structure becomes unstable. The protein malabsorption that begins immediately after acid loss doesn't just affect your muscles. It impacts every single organ system because proteins are the workhorses of cellular function. Your heart needs proteins to contract effectively. Your kidneys need proteins to filter blood. Your brain needs proteins to produce neurotransmitters. As protein deficiency progresses, your body's ability to produce enzymes, the biological catalysts that drive virtually every chemical reaction in your body, becomes severely compromised. This creates a cascade where not only are you not digesting food properly, but cellular metabolism throughout your body begins to slow down. The immune system represents one of the most protein-dependent systems in your body. Antibodies, complement proteins, cytokines, and cellular immune components all require adequate protein synthesis to function properly. As protein malnutrition progresses, immunoglobulin antibody production drops dramatically. These are your body's targeted weapons against specific pathogens. Without adequate immunoglobulin production, you become vulnerable to infections you've already been vaccinated against or have previously overcome. White blood cell function also becomes compromised. Neutrophils, your first-line cellular defenders against bacterial infections, require constant protein synthesis to maintain their pathogen-killing capabilities. Lymphocytes need proteins to produce the signaling molecules that coordinate immune responses. The complement system, a cascade of proteins that helps clear pathogens and damaged cells, begins to fail as its component proteins become deficient. This creates gaps in your immune defenses that pathogenic organisms can exploit. Paradoxically, while your immune system becomes less effective at fighting pathogens, it may become hyperactive in producing inflammatory responses. The constant bacterial challenge from your compromised digestive system, combined with increased intestinal permeability, triggers chronic inflammation that your weakened system can't properly resolve. The cardiovascular system faces multiple simultaneous stresses that compound each other in dangerous ways. Iron deficiency anemia forces your heart to work harder to deliver oxygen to tissues, but protein deficiency weakens the heart muscle itself, creating a devastating combination. As protein energy malnutrition progresses, your body may actually begin breaking down heart muscle protein to meet metabolic needs. This is like forcing your car's engine to burn its own components for fuel. It might work temporarily, but it guarantees eventual engine failure. Blood pressure regulation becomes compromised through multiple mechanisms. Protein deficiency affects the production of albumin and other blood proteins that help maintain proper fluid balance. Mineral deficiencies, magnesium, potassium affect electrical conduction in the heart. Chronic inflammation damages blood vessel walls. The blood clotting system also becomes dysfunctional. Many clotting factors are proteins that require adequate nutrition for synthesis. This creates a dangerous situation where you might bleed excessively from minor injuries, but also have increased risk of abnormal clot formation due to chronic inflammation. The nervous system faces a perfect storm of nutritional deficiencies that create cascading failures throughout neural networks. B12 deficiency alone would be devastating, but it's compounded by deficiencies in folate, thiamine, iron, and protein that all affect neurological function. The myelin sheaths that insulate nerve fibers begin deteriorating rapidly without adequate B12. But this process is accelerated by the lack of other nutrients needed for myelin maintenance and repair. It's like having electrical wires where the insulation is not just cracking, but actively dissolving. Neurotransmitter production becomes severely compromised because most neurotransmitters are made from amino acids which require protein digestion or require various vitamins as cofactors. Serotonin, dopamine, GABA, and other crucial brain chemicals can't be produced in adequate quantities. The chronic inflammation and nutritional deficiencies may also compromise the blood-brain barrier, the protective barrier that prevents harmful substances from entering brain tissue. This could allow bacterial toxins and inflammatory molecules to directly damage brain cells. The cognitive decline that begins with B12 deficiency accelerates as multiple other factors compound the problem. Poor oxygenation from anemia, direct toxin effects, inflammatory damage, and neurotransmitter deficiencies create a multi-front assault on brain function. The endocrine hormonal system depends heavily on adequate nutrition for hormone synthesis and regulation. Most hormones are either proteins themselves or require adequate nutrition for their production and function. Thyroid function becomes compromised through multiple pathways. The thyroid gland needs iodine, selenium, and tyrosine amino acid to produce thyroid hormones. Iron deficiency affects thyroid hormone metabolism. The chronic inflammation can trigger autoimmune thyroid disease. The adrenal glands, which produce stress hormones like cortisol, become exhausted from the constant physiological stress of malnutrition, infection, and inflammation. This creates a state where your body can't properly respond to additional stressors. Reproductive hormones shut down as the body recognizes that it doesn't have adequate resources to support reproduction. This isn't just about fertility. Sex hormones affect bone health, mood, cognitive function, and cardiovascular health. Growth hormone and insulin-like growth factor 1, IGF-1, decline dramatically in response to protein energy malnutrition. These hormones are crucial not just for growth in children, but for tissue maintenance and repair in adults. The skeletal system faces attacks from multiple directions simultaneously. Calcium malabsorption directly affects bone formation, but this is compounded by hormonal changes, chronic inflammation, and protein deficiency that all accelerate bone loss. Osteoblasts, bone-building cells, require adequate protein and various minerals to function. As these nutrients become deficient, bone formation slows dramatically while bone breakdown continues at normal or accelerated rates. The parathyroid hormone system, which regulates calcium balance, becomes disrupted. Low calcium absorption triggers excessive parathyroid hormone release, which pulls calcium from bones to maintain blood calcium levels. This creates a vicious cycle of accelerating bone loss. Vitamin D deficiency, which develops due to fat malabsorption, compounds all these problems. Vitamin D is essential for calcium absorption and bone metabolism, so its deficiency creates another layer of skeletal system failure. The kidneys face enormous stress from multiple directions. They must filter increasing amounts of bacterial toxins, inflammatory molecules, and metabolic waste products while operating with inadequate protein for proper function. The glomerular filtration rate, the kidney's ability to filter blood, begins declining as the filtration apparatus becomes damaged by toxins and inflammation. This creates a backup of waste products that further stresses other organ systems. Electrolyte balance becomes increasingly difficult to maintain as kidney function declines, and mineral absorption decreases. Sodium, potassium, magnesium, and phosphorus imbalances create additional stress on cardiovascular and neurological systems. Ironically, as kidney function declines, the body may develop metabolic acidosis. Too much acid in the blood, even though the stomach is no longer producing acid. This occurs because the kidneys can't properly excrete metabolic acids, creating a systemic pH imbalance. As multiple organ systems begin failing simultaneously, the body reaches a point where the cumulative stress exceeds its ability to compensate. This is when relatively minor additional stresses, a simple infection, a fall, or even emotional stress, can trigger catastrophic system failure. At this point, medical intervention becomes extremely complex because treating one problem often makes another worse. Antibiotics for infections worsen digestive problems. IV fluids stress the weakened heart. Nutritional support may not be absorbed effectively. The window for recovery narrows dramatically once multiple systems are failing simultaneously. Even if stomach acid production could somehow be restored, the damage to other systems might be irreversible, creating permanent disability or death despite correction of the original problem. This system's failure cascade demonstrates why stomach acid isn't just important for digestion. It has a critical component in the interconnected web of human physiology. Its loss triggers a biological catastrophe that ultimately threatens the viability of the entire organism. If you actually lost your stomach acid production, the medical community would face one of the most challenging clinical scenarios imaginable, trying to compensate for the loss of a fundamental biological function while managing the cascade of complications it creates. Let's explore the heroic but ultimately limited medical interventions that would be attempted. The first challenge would be recognizing what's happening. Dr. Maria Santos, an emergency medicine physician with 20 years of experience, explains, a patient presenting with the early symptoms of stomach acid loss would likely be misdiagnosed initially. Bloating, nausea, and digestive discomfort are common complaints that could indicate dozens of different conditions. The diagnostic workup would likely include complete blood count showing early anemia, comprehensive metabolic panel revealing electrolyte imbalances, inflammatory markers showing elevated inflammation, stool cultures potentially showing abnormal bacteria, upper endoscopy showing changes in stomach lining, gastric pH testing. The key diagnostic finding, the critical diagnostic clue, would be gastric pH monitoring. which would show a stomach pH of 6 to 7 instead of the normal 1.5 to 3.5. Dr. Robert Chen, a gastroenterologist, notes, finding a completely neutral stomach would be shocking. We'd probably repeat the test multiple times because it's such an unusual finding. Once the diagnosis is confirmed, the medical team would need to develop a treatment protocol for a condition that has no established standard of care. This would likely involve specialists from multiple disciplines: gastroenterology, digestive system management, infectious disease, infection prevention and treatment, nutrition, nutritional support and supplementation, hematology, management of anemia and bleeding disorders, endocrinology, hormonal complications, immunology, immune system support. The immediate priority would be nutritional support and infection prevention. This would likely require parenteral nutrition, bypassing the digestive system entirely by providing nutrients directly into the bloodstream through the lines. This would include predigested amino acids, bypassing the need for pepsin, essential fatty acids, vitamins, and minerals in readily absorbable forms, calories to prevent further muscle breakdown. Dr. Jennifer Kim, a clinical nutritionist, explains, we'd essentially be trying to replicate what a functioning digestive system does, but through for administration. It's possible short-term, but extremely complex and risky long-term. Given the severe compromise of pathogen defense, extreme infection control measures would be necessary. Isolation in a sterile environment, sterile food preparation, if any oral intake is attempted, prophylactic antibiotics, though this creates its own risks, constant monitoring for signs of infection, rapid response protocols for fever or other infection signs. The medication regimen would be extensive and complex, nutritional supplements, likely requiring injection or for administration, vitamin B12 injections weekly or monthly, iron infusions, oral iron wouldn't be absorbed, calcium and vitamin D high dose for formulations, folate supplements, thiamine and other B vitamins, magnesium and zinc supplementation, antimicrobial therapy, rotating antibiotics to prevent resistance, antifungal medications for yeast overgrowth, probiotics, though their effectiveness would be questionable, medications to treat small intestinal bacterial overgrowth, acid replacement attempts. Ironically, doctors might attempt to replace stomach acid artificially. Betaine hydrochloride supplements, though absorption would be problematic. Dilute hydrochloric acid solutions, extremely dangerous and likely ineffective. Pepsin enzyme supplements, though they wouldn't work without acid activation. Surgical interventions might be considered, though options would be limited. Gastrostomy tube placement, a feeding tube directly into the stomach to bypass swallowing and reduce bacterial contamination from oral flora. Small bowel feeding, tubes placed directly into the small intestine to bypass the now dangerous stomach environment. Potential experimental procedures, parietal cell transplantation, experimental and likely ineffective artificial stomach acid delivery systems, theoretical only gastric bypass. To minimize bacterial overgrowth, high risk as complications develop, intensive care would become necessary. Cardiac monitoring for arrhythmias from electrolyte imbalances, blood pressure support as heart function deteriorates, treatment for heart failure. From chronic anemia, mechanical ventilation if respiratory muscles weaken, treatment for pneumonia. From immune compromise, oxygen support for severe anemia, continuous assessment for cognitive changes, treatment for peripheral neuropathy, seizure monitoring and prevention. Renal replacement therapy as kidney function declines from chronic toxin exposure. Dialysis might become necessary to filter blood and maintain electrolyte balance. Drive. Santos reflects on the likely outcomes. Honestly, the prognosis would be very poor. We could potentially keep someone alive for weeks or maybe months with intensive medical support, but the quality of life would be terrible, and the complications would be relentless. If the patient survived the acute phase, long-term care would be extraordinarily complex, permanent for access, central venous catheters for ongoing nutritional support, with constant infection risk, isolation living, severely restricted lifestyle to minimize infection exposure, medication dependence, dozens of medications and supplements requiring careful coordination and monitoring. frequent hospitalizations, regular admissions for infections, complications, and monitoring. Experimental and future therapies. Desperate circumstances might justify experimental approaches. Stem cell therapy, attempting to regenerate parietal cells currently impossible with existing technology. Artificial organ development, working toward an artificial stomach acid production. Device purely theoretical. Gene therapy, attempting to restore acid production through genetic manipulation. Extremely experimental. Fecal microbiota transplantation, trying to restore normal gut bacteria, likely ineffective without acid barrier. The cost of managing complete stomach acid loss would be staggering. I see you care. $5,000 to $10,000 per day parenteral nutrition, $300 to $500 per day medications, and supplements, $200 to $400 per day. Specialized procedures and monitoring, hundreds of thousands annually. Dr. Kim notes, the annual cost could easily exceed $1 to $2 million per patient, and that's assuming we could actually keep them alive and stable. The harsh reality is that even with maximum medical intervention, quality of life would be severely compromised. Constant medical procedures and monitoring, severe dietary restrictions, social isolation due to infection risk, progressive weakness and disability, ongoing pain and discomfort, cognitive decline. From nutritional deficiencies, the medical team would face difficult ethical decisions. When to transition from aggressive care to comfort care, resource allocation in the face of poor prognosis, informed consent for experimental treatments, quality of life versus quantity of life decisions. Dr. Chen concludes, this would be one of the most challenging conditions we could face as physicians. We'd be fighting against fundamental human physiology with tools that simply aren't adequate for the task. It would highlight just how miraculous and essential our normal stomach acid production really is. The medical intervention scenario demonstrates that while modern medicine is remarkably advanced, there are some biological functions so fundamental that their loss creates medical challenges beyond our current capabilities to solve. While we've focused primarily on the biological consequences of losing stomach acid, the psychological and social impacts would be equally devastating. The transformation from a healthy, independent person to someone requiring constant medical support would create profound changes in mental health, relationships, and social functioning. Imagine waking up one morning as a fully functioning adult and, within weeks, becoming completely dependent on medical technology for survival. The psychological impact of this transformation would be staggering. Dr. Lisa Rodriguez, a clinical psychologist specializing in chronic illness, explains, patients who develop sudden, severe medical conditions often experience what we call biographical disruption. Their entire life narrative gets shattered. They have to rebuild their sense of self around their illness. The physical changes alone would be psychologically traumatic. Visible weight loss and muscle wasting, pale, unhealthy appearance from anemia, hair loss and brittle nails from nutritional deficiency, constant fatigue affecting all activities, cognitive changes affecting personality and thinking. The need for extreme infection control would create immediate social isolation that would compound over time. Food-related social activities. Nearly all social activities in human cultures revolve around food. Birthday parties, family dinners, restaurant meals, workplace lunches, all would become impossible or extremely complicated. Physical proximity restrictions. The need to avoid potential pathogens would require avoiding crowded places, limiting hugs and physical contact, and potentially requiring others to wear masks around you. Travel limitations. Any travel would become extremely risky due to exposure to unfamiliar pathogens and potential disruption of medical support systems. The cognitive and physical effects would make most forms of employment impossible. Cognitive impairment, B12 deficiency, and other nutritional problems would affect memory, concentration, and decision-making, essential functions for most jobs. Physical limitations, chronic fatigue, frequent medical appointments, and recurrent infections would make consistent work attendance impossible. Workplace safety. The immunocompromised state might make many workplace environments unsafe. The financial implications would be catastrophic. medical costs in the millions of dollars annually. Loss of income from inability to work, potential insurance battles over experimental treatments, need for specialized housing modifications, transportation costs for frequent medical appointments. The impact on family relationships would be severe and multifaceted. Family members would face enormous physical, emotional, and financial stress from caregiving responsibilities. Adult children might need to care for parents, or spouses might become full-time caregivers, fundamentally altering relationship dynamics. The infection control needs might require family members to limit their own social activities and potential exposure risks. Emotional labor, family members would need to provide constant emotional support while managing their own fears and grief about the situation. If the affected person is a parent, the impact on children would be particularly devastating. Constant anxiety about parents' health and potential death disrupted family routines and activities, possible behavioral problems or academic difficulties, premature loss of childhood innocence, financial stress affecting family. Lifestyle. The psychological impacts would likely include multiple mental health conditions, the combination of biological factors, nutritional deficiencies affecting brain chemistry, psychological factors, loss of identity and independence, and social factors, isolation and relationship strain would create a perfect storm. For severe depression, constant worry about infections, medical complications, and uncertain prognosis would likely lead to generalized anxiety, panic disorder, and health anxiety. The sudden, life-threatening nature of the condition and ongoing medical trauma could trigger PTSD symptoms. B12 deficiency and other nutritional problems could cause direct changes in personality, mood regulation, and thinking patterns. Dr. Rodriguez notes, patients with severe chronic illnesses often experience decision fatigue. The constant need to make medical decisions, manage treatments, and adapt to changing symptoms becomes psychologically exhausting. Providing mental health support would be complicated by several factors. Many psychiatric medications might not be properly absorbed due to digestive nutritional deficiencies, might impair the patient's ability to engage in traditional psychotherapy. In-person therapy might be risky due to infection concerns. Mental health providers would need specialized knowledge about the medical condition to provide appropriate support. Despite the overwhelming challenges, some people might develop adaptive coping strategies. Video calling and social media might become primary ways of maintaining relationships. Art, writing, or music might provide emotional outlets that don't require physical strength. Some might find meaning in advocating for research or supporting others with similar conditions. The confrontation with mortality might lead to spiritual development or philosophical insights. The severity of the condition would raise complex legal and ethical issues. Decisions about when to transition from aggressive treatment to comfort care would become critical. The cognitive effects might require others to make medical decisions on the patient's behalf. Desperate circumstances might lead to participation in experimental treatments with unknown risks. The enormous cost of treatment might raise questions about healthcare resource allocation and insurance coverage limits for those who survive the initial crisis. Long-term psychological adaptation would be a gradual process patients would likely go through. Stages similar to grief processing, denial, anger, bargaining, depression, and eventual acceptance. Life goals would need to be completely restructured around medical limitations and new realities. Finding purpose and meaning within severe constraints would become a central psychological challenge. Some individuals might develop remarkable resilience and find ways to thrive within their limitations. The development of support systems would be crucial for psychological survival. Relationships with healthcare providers might become primary social connections. Connections with others facing similar challenges could provide unique understanding and support. Families that successfully adapt might develop stronger bonds and new forms of intimacy. Involvement in advocacy for research funding or policy changes might provide purpose and community. Maintaining hope would be crucial for psychological well-being. Hope for future treatments or cures would be important for motivation to continue treatment. Small improvements in symptoms or function could provide significant psychological boosts. Finding ways to contribute to others or leave a positive legacy might provide meaning. Learning to find joy and meaning in small, present moments might become essential survival skills. The psychological and social impacts demonstrate that losing stomach acid wouldn't just be a medical condition, it would represent a complete transformation of human experience, affecting every aspect of psychological, social, and spiritual life. The resilience required to adapt to such changes would test the very limits of human psychological capacity. After exploring the catastrophic consequences of losing stomach acid, it's natural to ask, how can we protect and maintain this crucial biological function? The good news is that there are many evidence-based strategies to support healthy stomach acid production and protect this vital system. Stomach acid production is influenced by numerous factors, both within and beyond our control. Understanding these factors gives us insight into how we can optimize acid production and avoid unnecessary suppression. As we age, stomach acid production naturally declines. Studies show that about 30% of people over 60 have reduced stomach acid production hyperchlorhydria, and this percentage increases with age. While we can't stop aging, understanding this natural decline helps us take proactive steps to maintain digestive health. Many common medications can suppress stomach acid production. Proton pump inhibitors PPs, omeprazole, lansoprazole, esomeprazole H2 receptor blockers, ranitidine, famotidine, cimetidine antacids, calcium carbonate, magnesium hydroxide. Some antibiotics can alter gut bacteria and affect acid production. Chronic NSAID use can damage stomach lining and affect acid production. Dr. Jennifer Walsh, a gastroenterologist, emphasizes the key is using acid-suppressing medications only when truly necessary and for the shortest duration possible. Many patients stay on PP is much longer than needed, which can create the very problems we've discussed. Chronic stress significantly impacts stomach acid production through multiple pathways. Stress hormones can suppress digestive function. Chronic stress alters gut bacteria composition. Anxiety can affect eating patterns and food choices. Sleep deprivation, often stress-related, impairs digestive function. Proper nutrition plays a crucial role in maintaining healthy stomach acid production. Protein-rich foods, meat, fish, eggs, dairy trigger natural acid production. Fermented foods, sauerkraut, kimchi, kefir support overall digestive health. Ginger stimulates digestive enzyme production and gut motility. Apple cider vinegar may help with acid production, though evidence is limited. Bitter greens, arugula, dandelion, stimulate digestive secretions. Key nutrients for parietal cell function. Zinc, essential for parietal cell function, found in oysters, beef, pumpkin seeds. B vitamins, particularly B1, B6, and B12, support digestive function. Vitamin D deficiency is associated with reduced acid production. Magnesium, important for enzyme function in acid production. Foods that may impair acid production. Highly processed foods can disrupt gut bacteria balance. Excessive sugar may promote harmful bacterial overgrowth. Trans fats can increase inflammation and impair digestive function. Excessive alcohol can damage stomach lining and impair acid production. Eating habits that support healthy digestion. Eating regular meals helps maintain steady acid production. Avoiding extremely large meals reduces stress on the digestive system. Allowing 3 to 4 hours between meals gives the stomach time to empty and reset. Mindful eating practices, chewing thoroughly mechanically breaks down food and stimulates acid production. Eating slowly allows proper digestive hormone release, minimizing distractions during meals. Phones, TV supports proper digestion. Hydration considerations, drinking large amounts of water with meals may dilute stomach acid. Staying well hydrated between meals supports overall digestive function. Room temperature beverages may be gentler than ice-cold drinks during meals. Regular physical activity supports healthy stomach acid production through multiple mechanisms. Exercise benefits for digestion, improves blood flow to digestive organs, reduces stress and cortisol levels, promotes healthy gut bacteria diversity, supports regular bowel movements and digestive timing. Timing considerations, Light movement after meals like walking can aid digestion. Intense exercise immediately after eating may impair digestion. Regular exercise routine supports overall digestive health since stress significantly impacts stomach acid production. Stress management becomes a crucial component of digestive health. Meditation and mindfulness activates the parasympathetic nervous system, which supports digestion. Deep breathing exercises can be done before meals to promote digestive readiness. Regular sleep schedule. Adequate sleep supports healthy hormone regulation, social connection. Strong relationships reduce stress and support overall health. Sleep and circadian health. Poor sleep quality can impair digestive function. Aim for 7 to 9 hours of quality sleep. Maintain consistent sleep and wake times. Avoid large meals close to bedtime. Create a relaxing bedtime routine. Regular medical care can help identify and address issues before they become severe. Include assessment of digestive symptoms. Check for B12, iron, and other nutrient levels. Regular assessment of whether acid-suppressing medications are still needed if indicated by symptoms or family history. When to seek medical attention. Persistent digestive symptoms, bloating, nausea, early satiety, signs of nutritional deficiency, fatigue, pale skin, brittle nails, recurrent infections or unusual illness patterns. Difficulty maintaining weight despite adequate food intake. Supporting a healthy gut microbiome indirectly supports stomach acid function. Probiotic strategies, yogurt, kefir, kombucha, fermented vegetables, fiber-rich foods that feed beneficial bacteria may be helpful, especially after antibiotic use. Use only when medically necessary. Several environmental factors can impact digestive health. Choose organic foods when possible to reduce pesticide exposure. Filter drinking water to remove chlorine and other chemicals. Avoid unnecessary chemical exposure. In household products, be mindful of medication interactions and side effects as our understanding of genetics and personalized medicine advances. Individualized approaches to digestive health become possible. Some people have genetic variations affecting acid production, nutrient absorption. Genetics can guide supplementation strategies. Medication metabolism. Genetics can inform treatment choices. Since stomach acid production naturally declines with age, older adults may need special consideration. Strategies for older adults. More frequent monitoring of nutritional status. Consideration of digestive enzyme supplementation. Careful medication management. Attention to signs of malabsorption. Regular assessment of cognitive function. B12 deficiency screening. Digestive health often runs in families, making family-wide prevention strategies valuable. Shared healthy meal planning and preparation. Family stress management and mental health support. Education about digestive health for all family members. Creating supportive environments for healthy lifestyle choices. Research into digestive health continues to advance, offering hope for better prevention and treatment strategies. Emerging areas of research. Microbiome-based therapies. Personalized nutrition based on genetic profiles. Advanced probiotic formulations. Novel approaches to supporting parietal cell function. Better understanding of the gut-brain connection. The prevention strategies demonstrate that while losing stomach acid would be catastrophic, there are many evidence-based approaches to maintain and support healthy acid production throughout life. The key is adopting a comprehensive approach that addresses nutrition, lifestyle, stress management, and appropriate medical care. As we reach the end of our journey through this biological catastrophe, it's time to step back and appreciate the profound miracle of stomach acid, a substance so powerful it could dissolve metal, yet so precisely controlled that it operates safely inside our bodies every moment of every day. What we've discovered through this thought experiment is that stomach acid is far more than just a digestive aid. It's a master regulator that orchestrates protein digestion, pathogen defense, nutrient absorption, immune function, and microbial balance. It's the conductor of a biological symphony where every note must be perfectly timed and harmonized. The loss of this single function would transform a capable, independent human being into someone requiring constant medical support just to survive. It would take us from the top of the food chain to one of the most vulnerable organisms on the planet. less capable of surviving than many bacteria and viruses that stomach acid normally destroys, without us ever knowing they were there. From an evolutionary perspective, stomach acid represents one of biology's greatest innovations. It allowed our ancestors to safely exploit protein sources that would have been lethal to other species. It gave us the nutritional foundation to support large, energy-intensive brains. It protected us from pathogens that could have driven our species to extinction. The fact that our most advanced medical technology cannot adequately replicate or replace stomach acid function speaks to its remarkable sophistication. We can transplant hearts, replace kidneys, and even modify genes. But we cannot recreate the elegant simplicity of parietal cells, producing hydrochloric acid at precisely the right time, in exactly the right amount in perfect coordination with dozens of other digestive processes. Every meal you enjoy, every glass of water you drink from a questionable source, every social gathering centered around food, all of these common human experiences are made possible by the tireless work of your stomach acid. It's the unsung hero that allows you to live without constant fear of food poisoning, nutritional deficiency, or digestive failure. Think about the freedom stomach acid provides. Children can play in dirt. Adults can travel to foreign countries. Families can share meals without extensive food safety protocols. All because stomach acid provides a robust biological barrier against the countless pathogens we encounter daily. Yet in our modern world, we routinely suppress or ignore this crucial function. Millions of people take medications that reduce stomach acid production, often for longer than medically necessary. We treat acid-related discomfort as a simple inconvenience rather than recognizing it might signal that something important needs attention. This isn't to say that acid-suppressing medications don't have their place. They can be life-saving for people with severe GERD, peptic ulcers, or other conditions. But our journey through the consequences of acid loss should give us a deeper appreciation for the careful risk-benefit analysis that should guide these decisions. The good news is that stomach acid is remarkably resilient when we give it the support it needs. Proper nutrition, stress management, appropriate medication use, and healthy lifestyle choices can maintain robust acid production throughout most of our lives. Understanding the critical importance of stomach acid empowers us to make better decisions about our health. We can work with healthcare providers to ensure acid-suppressing medications are used appropriately. We can adopt lifestyle practices that support healthy digestion. We can recognize early warning signs that something might be wrong with our digestive system. Our exploration of stomach acid's importance also highlights how much we still have to learn about human physiology. The intricate connections between digestion, immunity, nutrition, and overall health continue to surprise researchers and reveal new therapeutic possibilities. As our understanding deepens, we may develop better ways to support stomach acid function, more precise treatments for acid-related disorders, and improved strategies for maintaining digestive health throughout the lifespan. Perhaps most importantly, understanding the catastrophic consequences of losing stomach acid should give us a profound appreciation for the remarkable machine that is the human body. We often take our basic biological functions for granted until they fail. But stomach acid represents just one example of the countless miraculous processes occurring in our bodies every moment. The next time you sit down to a meal with family or friends, take a moment to appreciate the complex biological orchestra that will spring into action the moment food enters your mouth. Your brain will signal your stomach to prepare. Your parietal cells will fire up their proton pumps. Your stomach will transform into a precisely controlled chemical reactor that will safely process whatever you've chosen to eat. Even as you sleep tonight, millions of cells in your stomach lining will continue their tireless work, producing the acid that protects you from pathogens, enables proper nutrition, and maintains the delicate balance of your internal ecosystem. They'll do this without your conscious thought, without your thanks, and without fail, day after day, year after year. Our journey through the consequences of losing stomach acid also illustrates a broader truth about human biology. We are incredibly complex systems, where every component depends on every other component. The loss of any single critical function can cascade through multiple systems and threaten the viability of the whole organism. This interconnectedness is both our greatest vulnerability and our greatest strength. It makes us susceptible to cascade failures, but it also gives us remarkable resilience when all systems are functioning properly. As we conclude this exploration, consider what actions you might take to protect and support your stomach acid function. Review any acid-suppressing medications with your healthcare provider. Adopt stress management practices that support digestive health. Choose foods and eating habits that promote healthy acid production. Stay informed about the latest research on digestive health. Appreciate the remarkable biological processes that keep you healthy every day. Share this knowledge with others. Help people understand that stomach acid isn't just an inconvenience that causes heartburn. It is one of the most important biological functions we possess. The more people understand its critical role, the better decisions we can all make about our digestive health. As we finish our thought experiment, your stomach acid continues its essential work. Right now, as you process this information, your parietal cells are standing ready to produce the acid that will protect and nourish you with your next meal. This miracle of biochemistry, refined by millions of years of evolution, continues unabated. The catastrophic scenario we've explored, the complete loss of stomach acid, serves as a powerful reminder of how precious this function truly is. In imagining its absence, we gain a deeper appreciation for its presence. Your stomach acid may be invisible, it may work without fanfare, and it may seem like a simple function, but as we've seen, it's anything but simple. It's a biological masterpiece that deserves our respect, our protection, and our gratitude. Take care of your stomach acid, and it will take care of you. This ancient biological guardian has protected our species for millennia, and with proper care and understanding, it will continue to protect you for years to come. The next time someone complains about stomach acid or heartburn, you'll know the truth. They are not complaining about a problem. They are experiencing the power of one of biology's most important innovations. And that's something truly worth appreciating. Thank you for joining me on this journey through the catastrophic consequences of losing stomach acid. I hope it has given you a new appreciation for the remarkable biological processes that keep us alive and healthy every day. Until next time, keep questioning, keep learning, and keep marveling at the incredible machine that is the human body. Don't forget to like this video. If it changed how you think about stomach acid, subscribe to Sleepy Scientist for more thought-provoking explorations of human biology, and let me know in the comments what other biological functions you'd like to explore. What would happen if you lost your ability to produce insulin? What if your kidneys stopped filtering blood? What if your immune system shut down completely? The human body is full of critical functions we take for granted, and each one has a story as fascinating and important as the one we've just explored together. Sweet dreams! And remember, your stomach acid is working hard to keep you healthy even while you sleep.